Today I'm happy to introduce Josh Veers, who's a friend of mine. I was on the search committee at Merced that hired him. Josh is now the director, the citrus director at Merced. He's joined our team with water informatics. He has degrees in ecology and international agricultural development, which certainly is a big important thing with the changing climate. He had leadership roles at the Center for Watershed Science, and he was the executive associate director, and he was on the graduate education committee at Davis. So, Josh?
Thanks. I think we're good to go. Thank you so much, Steve. It's a real pleasure to be here. Can everyone hear me okay? Super. In Drought and Deluge, how applied hydroinformatics are becoming standard operating data for all Californians. I was inspired by this idea of drought and deluge because fundamentally California either has too much water or not enough, and there really is nothing in between. And so I'm going to spend a bit of time exploring how data can be informative in this case, and it's fairly central to my research, which is how to use better information, not necessarily more, but better information to have better decision making. As Steve mentioned, I'm now the director of citrus at the University of California, Merced, the UC's 10th campus. We're a rapidly growing institution with about 6,000 students and hurtling towards about 10,000 within the next 5 years. We have a number of signature issues at this campus, but increasingly water is a fundamental defining element of our research, education, and outreach mission. And so I'll talk a little bit about the direction that's heading. But first I'd like to take a moment to recognize all the others that have contributed substantially to the work that I'm going to show. One of those is in the audience, Dr. David Reinheimer, who's on as a postdoc here at Citrus, and will be available for questioning afterwards if you're interested in the direction that work's going. Nick Santos and Andy Bell at the Center for Watershed Sciences at UC Davis, and then my colleague at UC Merced, Roger Bales. I'll present just briefly some of his work that ties some of this together. I'd like to begin by talking about California water as this photo. When you are in other parts of our nation, oftentimes when they envision California, it's surfboards and palm trees and perhaps water parks. And in fact, I think this is a highly representative photo of how water in California works, namely that there is a system of tubes and tunnels that push water to a common pool resource with a number of consumers that use it to satisfy their desires. In this case, probably more fun than anything else. And this is all well and good, of course, until the water runs out. And so as you've probably seen in the news, California is either in the third or fourth year of either a 3 or 4 year drought that continues on. It's important to recognize that drought is a relative term, and you don't really recognize that you're in it until it's too late. At least that is the standard operating procedure for today, and it would be my hope that in the future perhaps that would change, that in fact we might be able to anticipate these conditions before we were in them. So I'll be presenting a number of hydrographs as we go forward, and fundamentally a hydrograph is some sort of pictorial depiction of water. It gets down to the fundamentals of hydros and the Greek root on that word, such that it's something that we can identify with. It's ubiquitous on this planet. It's a ubiquitous part of our bodies. Water is fundamental to life. And in this cartoon, the Dutch geographer Henrique van Loon sketched North America in such a way that I find a hydrograph hidden among these many mountains. And I think it's fairly easy to see the Mississippi-Missouri complex and the Great Lakes and these dendritic drainage patterns that mark the surface of our continent. But what I also see on the Pacific coast I see the Coast Range, I see the Intermountain West, and I see an orange area. And of course, that orange area depicts the arid West. And if you think about the westward movement of America as it stretched across the continent before it hit the Pacific Ocean, that journey was an arduous one, and it was one that was bereft of water. Fundamentally, people were seeking a new life, but it was difficult to get there in part because there was very little water. Until they reached California, until they reached the Sacramento River and the San Joaquin River. And you can see them in this cartoon as they come together to form the Sacramento-San Joaquin Delta, which remains today the hub of our water infrastructure in the state of California. There's a different type of hydrograph, and that's the one that's often depicted by these data that we use in analyses, that we use to teach undergraduates fundamentals of hydrology. It's depicted here as that blue line. And that blue line can be characterized by its magnitude, how big was a flood, the frequency, the timing, the duration, and the rate of change. Fundamentally, we refer to this as the natural flow regime, and we can characterize any given water body that moves through time. A fluvial river system is the amount of water or discharge that flows through time and over space. That remains a fundamental challenge for managing water, in part because we need to anticipate how much, where, and when. There's either too much water or not enough. And such is the case of the Cosumnes River in central California that joins the Sacramento and the San Joaquin at its delta. It remains the only undammed river on the west slope of the Sierra Nevada. In fact, it's only undammed because it was the ugly duckling. It had the lowest yield. It didn't have a good place for a dam. It has a low crest elevation. There wasn't much snowpack. There wasn't much to dam. But because of that, it still retains that natural hydrograph. It has the frequency, the duration, the magnitude, the rate of change that we find in natural systems. And increasingly that's becoming important because we have to look back to nature to provide guidance as to how we can manage our water resources. I put to you, is this a hydrophotograph? It's a hydrograph of a different sort, right? So photographs are elements that tell us a little bit about the state of a system at a given point in time. Here we have the quantity of water moving through space at a fixed point in time. And that's something I'll come back to at the end of this talk. So fundamentally, California has either too much water or not enough, and increasingly, given hydroclimatic alteration due to global climate warming, we're seeing things that have never seen before. Here, in 2012, we had a 10-year event. So 90% of all the flows in the Yuba River in this particular case were less than this particular flood event. Now, keep in mind, this was 2012, and this is part of that drought that I mentioned in the beginning. So we're seeing an extreme flood during a drought year. Juxtapose that with a dry riverbed in the Cosumnes River, which is the last free-flowing river in the Sierra Nevada. However, there is no flow. And fundamentally, this was during a wet year of 2006. And so hydrologic alterations taking place in this case on a regional scale due to groundwater depletion that have lowered the water table such that this river now runs dry during the summer. So being able to understand the dimensionality, the timing, the frequency, the volume in space and time remains a fundamental challenge to water resources management. Fast forward to today, where we're using advanced techniques, in this case, a small unmanned aerial vehicle mounted with a camera, again, a hydrophotograph, to examine the reconnection of the Cosumnes River, here shown at the bottom of the photograph, to its river channel to end the drought, right? So in this case, the Cosumnes River riverbed had been dry for several hundred consecutive days. And this histogram clearly depicts what is a bimodal distribution. Most of the time, the number of days in which this river runs dry is close to 10, 20, or 30. Other times, It could be 150 days or more, but there is some bimodality there to suggest that these periods of drought, in fact, are quite common. And if you look at the hydrological record, you'll see that the drought that we are in today happens about every 30 years. That's fundamental information that we need to know in order to manage our water resources more effectively. I'd like to also point out the outlier. For those of you who like to look at distributions, you'll see this one that occurred in the 1976-1977 drought that was nearly 600 days long of a dry riverbed. So you can imagine it's difficult then, if you're a fish, to make a living in this river. So what is hydroinformatics? In fact, it's just what it says. It's information about water. It's about the volume of water, how it moves through space and how it moves through time, but in a way that can be synthesized such that we could look at a particular threshold to say that when there's enough water to access a floodplain, interesting things happen. Those interesting things can be primary productivity, it could be fish spawning, it could be recharge of our local aquifer. However, that's information that we need to know and currently are challenged to do so. It's surprising, in fact, that we have so little information when it comes to water because it is so critical to this state. As it turns out, about 2/3 of all of the runoff, the water that falls on land and runs off and is often captured and used for human uses, 2/3 of all that water happens north of Sacramento. So the areas depicted in blue, in fact, are 90% of all the runoff, and it happens on only 40% of the land surface. And because of that, we have one of the most vast engineering works in the world where we capture, store, divert, and deliver surface water to places that need it most, and 60% of that is south of Sacramento. So there's a physical disparity. We have to move water from a place of abundance to a place of scarcity. Because of that, we now face a number of challenges. Where does that water go? Fundamentally, it goes to people. We're hurtling towards a state of 50 million people, right? But where are those people located? Primarily in coastal areas, such as the Bay Area, such as the Los Angeles metropolitan area, but increasingly urban centers within the Central Valley, and of course, so much of that water actually goes to agriculture. So of all the developed water that's used for human uses, 80% of that consumptive use is for agricultural irrigation. We produce half of the nation's fruits, nuts, and vegetables. It's a $30 billion economy. It's a critical need that at present we have very little information with respect to how much water we have and where it goes. In the process, of course, of developing that vast engineering works, we developed a number of dams, and in the course of developing those dams, we've had a number of negative effects on aquatic ecosystems. So increasingly, we're looking to aquatic ecosystems as the canaries in the coal mine, not just because of the quantity of water moving through the system, but the quality of water. And if you were to look at the decline of California's native fishes, it isn't just these salmon runs, which are now extirpated from those lines turned red that used to be blue, but it's across the entire suite of those native species. So from 1989 through 2012, the number of reasonably secure species has decreased by half. We've gone from 44 to 22. And the number of species that are now listed as either threatened or endangered under the Endangered Species Act has increased sixfold. These are the canaries in the coal mine, and what they suggest is the way that we're managing our water is not compatible with their future existence. However, there remains a fundamental problem with this, is that at present we know very little about the nature of this particular problem. In part because we know something about the status of these fishes, but we don't know where they are. So we know that anadromous species, the ranges have contracted on over 50%. We also know that dams are largely responsible for that. And we also know that all of the other taxa, the 120-some native species found in California, are in serious decline. But what we cannot tell you is where that's happening. We can tell you that there are over 3,000 major dams in the state of California, and we know to some extent where that is. There are about 40 million acre-feet of water storage, which is over half of the amount of runoff in the state that is impounded. It's that capture, diversion, delivery that takes place. So what if we were able to leverage information in such a way so that we knew where those dams were, but we also knew where the impacted ecosystems were? Could we say something meaningful for that? In order to do this, in order to provide the state of California with some knowledge as to where those fishes were, we developed some software known as Pisces that captures the information as we know it about all of these native fishes. That software is not only just a database that houses those, but a number of interactive plugins that can capture data from disparate sources. So we're talking about empirical observations, such as XY coordinates from a GPS unit, from expert knowledge. If someone who happens to know a particular species very well and where it's distributed, or even models. If we can infer where a particular species would like to be based on its environmental requirements, we capture all of that into a database, a spatially enabled database, and then can make a number of informed decisions about where those species are. This map depicts the state of knowledge as we know it today, over 120 native species combined with almost 60 non-native species, and the areas in red show the highest richness, or the total number of species for a given unit area. And you can see that the area in red is the Sacramento-San Joaquin Delta. The system also allows us to look back through time. We can look at the historical distributions of fishes. We can look at the current distribution of fishes. We can look at those exotic non-native fishes that were introduced primarily for sport fishing, but through just simple subtraction. We can then also look at those species that have been extirpated through time. So we've lost over 8 species of native fishes from California. A couple of those have gone extinct forever. This is a critical moment in our state's history as we begin to grapple with meeting the water demands and needs of humans with those of ecosystems. So perhaps we can combine then that information about the water infrastructure, such as dams, with information about ecosystems, such as sensitive species of concern in relation to dams, and combine those in innovative ways. Ultimately, we'll be asked, how can we operate those dams in a more effective manner? And to do that, we need to know how much water actually arrives to those dams and that infrastructure. And this information, too, has been lacking until now. We know that it's highly variable over space and over time, that in some years we get a lot of water, and other years not so much. This map depicts the mean annual surface runoff unimpaired that arrives to a given watershed cumulatively. So then we can actually combine this information with the amount of water that we give away, right? So water rights in California are combined of what they call riparian rights, meaning that if you're adjacent to the river, you have some right to use the water as it flows by. And appropriated water rights, meaning that if you were the first in time, you were the first in right to use that water. And this was highly utilized throughout the western United States, particularly for things like mining, which is the history of the state of California. So by 1920, we had allocated tens of thousands of acre-feet to particular water right holders. If you were there prior to 1914, you were grandfathered in. So these data don't even show some of the oldest water rights in this state. But if we were to step through time and begin to accumulate what we refer to as the face value of allocation through these water rights, you can see that the number of rivers that have been allocated for the full natural runoff becomes increasingly large. And as we get to today, you can see that many of these watersheds, in fact, are tens of thousands of acre-feet, and acre-feet being the amount of water that can satisfy a family of 4 for a year. That all across the state, we've allocated this water, and in fact, we continue to allocate this water today. We've given away 370 million acre-feet of water on paper. Now keep in mind, on a good year, there's about 70 million acre-feet of surface water runoff in this state. So over 5 times the amount of runoff that's available in a good year has been given away on paper to a number of water rights holders. Unfortunately, we don't even know if they use this water. Unfortunately, we continue to give more rights away today, and if you look at this cumulative distribution function for the number of water rights filed, we continue, there is no asymptote, we're going to continue to increase in value, and the cumulative volume associated with that also is increasing. And I think we're finally at this point where information is coming to bear in such a way that we can make some informed decisions about that. So if we knew the mean annual flow cumulatively for a given place, and we knew the allocation of water for a given place, we could begin to synthesize this information in such a way to say that those rivers in red, which have a lot of runoff, also have a lot of that runoff allocated. So the ones in red represent those rivers that have 100 to 1,000% of their full natural flow allocated to humans. It's no surprise then that the areas in and around the Sacramento and the San Joaquin River and their delta are so compromised. To further complicate this matter is that the policies that we have in place to issue water are antiquated at best, primitive, and inflexible. Perhaps most fundamental to this is what we refer to as water year typing, which is to say that we have 4 major rivers that we use for Northern California to type a given water year, and we have 4 major rivers in the San Joaquin Valley that we use to type a given water year. And if we project forward with hydroclimatic alteration due to global warming, this inflexible nature for water year typing is likely to be compromised. So looking at a number of GCMs in an ensemble type forecast, we calculated the frequency with which we have a wet year, a normal year, or above normal year, below normal, dry, and critically dry. It's important to point out that of those 5 water year types, normal is not one of them. And what had been a uniform distribution of water year types is likely to run bimodal by mid-century, meaning that it's either going to be wet or critically dry, and these forecasts suggest that by end of century, they're going to be disproportionately critically dry. Now, there's an important caveat to this, and that is that the very formulation of the index that they use to type a given water year is heavily weighted toward the snowmelt portion of our hydrographs. So 60% of that index value is based on an April through July runoff. What we do know about climate warming and how it interacts with California's water and hydrological system is that we anticipate less snow and more rain. So as the atmosphere warms, there's going to be less snowpack, more rain moving through the system, and most of that's going to happen in the winter months. So if precipitation were to be kept constant, we would still see a trend towards dry. And one of the things that we know is that when things tend toward dry and water becomes increasingly scarce, there are winners and there are losers, and oftentimes the environment is the loser. One example of this is the Foothill yellow-legged frog. It's found in the foothills of the Sierra Nevada. It's the only river-breeding frog in the Sierras, and it's highly dependent upon that snowmelt recession signal. It's cued for its timing for reproduction to lay eggs on the margins of rivers, and as those eggs metamorphose into tadpoles, the tadpoles are able to then slowly make their way into the river as they get larger. Unfortunately, however, river regulation, now keep in mind that most, if not all, the rivers in California are heavily regulated throughout their length, is that river regulation is fundamentally at odds with that natural flow regime, either through diversion, so that there's little to no water in that river, or hydropeaking or pulse flows that do not actually represent what we might find in terms of the magnitude, timing, frequency, and duration of a natural flow regime. So where to from here? Well, one of the things that we've been able to recognize then is that the chaotic flows of the winter time that are high in magnitude and have a lot of abiotic disturbance and moving rocks and sand and so forth, is a period of disturbance that most species are well adapted to. We also know that during the summer period of low flows, that these species experience a high level of stress, oftentimes through competition or environmental stresses such as increased water temperature. But it's that snowmelt recession portion of the hydrograph that is non-limiting and predictable and very stable. So perhaps with better tools and better information, we could begin to assess the snowmelt recession period in a way that's more meaningful for a frog. Again, back to a hydrograph. Can we mimic that natural hydrograph in such a way as to identify the amount of water in space and time and the amount of habitat associated with that given species? To help answer that very question, we developed some software called Streamlapse, which is an amalgamation of images taken from a remote video camera, in this case, a still image taken once an hour, that is collapsed into a video stream and combined with either discharge data from a logger or stage data from a logger and superimposed on top of that video stream, such as to be able to visually appreciate the hydrodynamics of a given site. So as we step through this video, you'll see a number of data being visualized. On the left-hand side, we have the Clavey River, which is an unregulated river system. And on the right-hand side, we have the Tuolumne River, which is downstream of the Hetch Hetchy Dam, O'Shaughnessy Dam and the Hetch Hetchy Reservoir. And one of the things that you'll notice is that there we had a big pulse in the Clavey River that did not show up on the Tuolumne River. And it actually didn't even show up on the gauge data upstream to suggest that there was a localized precipitation event of low elevation that was able to flow through the Clavey River that was not present in the Tuolumne River, in part because of the water management scheme. This hydrograph shown in blue is synchronized with each one of those snapshots, and superimposed on top we have water temperature shown in orange and air temperature shown in green. And as we move through February and on into the early spring, you'll see that air temperature and water temperature are highly synchronized. And we can see that during that kind of late winter period, moving into spring, that flows remain relatively low. One area to focus on here is this gravel bar. You'll begin to see that it gets covered by these different events. And you'll see that the tributary, which is the Clavey River as it comes in, will be either in phase or out of phase with the main stem Tuolumne River. Here, providing visual evidence as to how much habitat is available to river-breeding frogs, fishes, and other ecosystem components. As we move toward the snowmelt recession period of the hydrograph, we're now into April. You'll see humans starting to use this river in ways that have to do with recreation. It's whitewater boating. And that remains an important part of the economy of the Tuolumne River watershed that recently experienced the rim fire that you may have heard about. It's now compromised that particular activity. But it's this visual evidence that will be able to help water managers better appreciate how river management below dams affects downstream ecosystems. So we just had the big snowmelt pulse on the Clavey River, and as that blue line begins to recede, you'll see that there's a diurnal fluctuation there. So each day we have a pulse of snow that gets melted and moves through the system. We're able to actually figure out from that frequency what the travel time is in that system. From the color photographs on the right, you get a sense as to the turbidity or the water clarity of that river system. Again, it also has a diurnal flux for that. As we get toward the end of the spring, we're now in late May, early part of June, you'll see that the Tuolumne River has gone from high flows to very low flows. And this is the period in time in which water resource managers no longer fear flood. right? So in drought and in deluge, they're now managing for scarcity and an annual drought that we refer to as summer. You'll notice that on the left, the Clavey River continues to recede. It has not quite reached that low flow period. You can see that the air temperature and the water temperature are decoupled, but still interacting on a diurnal basis. That natural signal is very evident. Whereas on the Tuolumne River on the right, we can see that the amplitude of this diurnal flow is out of phase with what we might see in a natural system. The reason being is that they are releasing water each day for one purpose, and that purpose is for whitewater rafting. So as you see, each of these boats show up here at the confluence in a camp that we call Clavey Right, and some of them going through the whitewater rapids there. Each day, the water managers for the city of San Francisco release a block of water such that the boats can get over these rocks. Because that water is held behind a dam, its thermal properties are very different. There's a hypolimnion layer at the bottom of those dams, and it's very cold water. You can tell from the endpoint here that air temperature shown in green is decoupled from the water temperature shown in orange, which is fundamentally related to the amount of water moving through the system from this managed perspective, as opposed to the natural hydrograph where we see the air temperature, water temperature coupled to each other and a slow, gentle recession. So this hydrolapse videography and the software called Streamlapse are being used in other river systems throughout the Sierra Nevada, such as the American River System, the Yuba River System, and the Cosumnes, to be able to understand hydrodynamics, to be able to understand the amount of water moving through space and through time in a way that is both contextual from a qualitative standpoint and also provides the necessary numerical information to be quantitative. Can we use this information in a meaningful way going forward? Well, we need to be able to do this in such a way that all of the different components can come together. Some of that might be remote sensing from snow water equivalent. It could be hydrologic modeling and analysis, estimation of uncertainty, real-time forecasting, and ultimately taking that information, better information, and using that for better decision-making. So Citrus is leading the way in many respects to bring hydroinformatics to the fore of decision-making for water in the state of California, being led by Roger Bales and Steve Glazer, and being able to bring information about snow to the place that needs it most, which is in the decision of how much water to release, where, and when, and that's information that's been sorely lacking as we go forward. And so in the development of new water measurement technology, whether that's remote sensing from satellites or aircraft, wireless sensor networks, and different modeling tools, that information is now coming together in such a way that we'll be able to trace that water droplet from when it falls on the crest of the Sierra Nevada to when it either outflows through San Francisco Bay or ultimately ends in that swimming pool in Southern California. In closing, I'd like to use another cartoon, which I think is highly indicative of where the state is today, where many of us in the state ask a simple question: how do we get water into our homes? Right? We know that it rains and then it comes out of a faucet, but what happens in between? And those are the gaps that we're currently trying to fill. So with that, I'll say thank you and take questions.
So if you can use the mic if you have any questions. Any questions, Steve? Oh, questions over here.
So you showed that curve that we have ever more water rights being allocated.
That's
so
right.
I'm really puzzled by that. I mean, if you're already kind of a water shortage, who is the group or person that gives away something that they don't really have? And what's behind that?
Yeah, that's a great question, and thanks for asking it, because I didn't provide as much detail on this database. So the State Water Resources Control Board, which is a state agency, has a database that they refer to as ERIMS, which is a Water Resource Information Management System, and there's a silent E in the front. This database tries to collect all of these water rights databases that have been allocated by the board. Now, there is some complexity to these water rights, and in some cases, they could have multiple points of diversion. In some cases, these water rights have been issued but never exercised. Fundamentally, the numbers that I showed do not show water rights that were issued prior to 1914, nor those riparian rights. So suffice it to say that's actually incomplete accounting. But if you were to take all of those water rights, some 30,000 in number, and 370 million acre feet in total allocation, there is a fundamental disconnect between the water rights system as it's being implemented and the reality of how much water is actually available. The other thing to keep in mind, however, is that in an appropriate water rights system, we have senior water rights holders and junior water rights holders, which means that you could have a right to that water but never be able to use it because the person standing in line before you used what was available. In many cases, however, when it's allocated 7 times over, even with some water reuse as it moves through the system, it would be impossible to have that much water physically to be able to allocate in its full face value. And I think that's the point that we try to make. And as the state actually moves forward, and they're in the position now of trying to scale back how much water people are, can take, even if they're, allocated 100,000 acre feet, they're in a senior water rights holder, they're now being told that they might have to pull back by 50%. Is that there's no fundamental way for them to know who, among that pool of water rights holders, should be restricted, and where, and how much is actually available. So there's a fundamental disconnect in our information system to be able to handle this. And further, to get to that point about water year typing, is that there are these very arbitrary rules that say if it's a wet year, everybody gets some. If it's a dry year, not everyone gets some. But because that's an arbitrary threshold, it would just take one rain event to push you into a new category, or the lack of one rain event to push you into a different category. And as we go forward into an era in which we refer to as non-stationary, meaning that the future is not likely to be represented by the past, that type of inflexible policy setting will work against us. Yeah.
I'm very excited to see the ERL paper. It looks like a fantastic data set. And one of the things I noticed, it went by a little quickly, but it looked like the red bin there was between 100 and 1,000% of average flows. And I'm curious if you can talk a little bit about what it looks like within that, because there's a huge difference between 100% allocation and 1,000. You could have over 100% allocation that would work in an average year because return flows would run off of one field and into the stream and could be used multiple times. But how would you sort of ask questions about where is the viable amount of water rights given the types of water uses that are happening, and what are we actually seeing?
Yeah, that's a great question, Mike. Thanks for bringing that up. And that particular map, one of the things to keep in mind is that the full natural flow was estimated from a statistical algorithm called random forests and was generated by USGS and includes a number of land use parameters and climatic parameters to arrive at that number. We're allocating what are referred to as these HUCs, or hydrologic unit codes, developed by USGS as to what that full natural flow would be, and then summarizing the allocation per HUC. And there's a bit of a spatial imprecision, you might say, in that there may be a water right within that HUC that isn't directly on that river being affected. So this is an approximation of that full natural flow cumulatively and the face value of that. So I think we weren't in the position to say which individual streams being affected by that. Now, that being said, this paper is being used as the basis to approach the state board, which are now in the process of trying to leverage their database in a more meaningful way. And I think the target watershed is going to be the Russian River. Don't hold me to that, but that's a very contentious area in the state, often because water is used for frost protection during the springtime to protect wine grapes, but it's also a time when native coho and steelhead salmon are at a critical life history stage. So I think this paper in particular was just to point out that this information store is really inadequate for making decisions. But I think your point's well taken that being able to evaluate how much reuse could possibly take place physically and anything above and beyond that would be too much. I don't think we're quite at that point to do that synoptically across the state, but for individual systems, possibly so.
Just one more question about these water rights. Is there a secondary market, and is it regulated in any way?
Excellent question. So the question had to do with, is there a secondary market, meaning could you resell those water rights? And the answer is yes, to a limited degree. And it requires infrastructure. For water rights holders that are part of that vast engineering works where we do transfer water to and fro, there is, in some cases, the physical infrastructure to transfer water from one place to another. Oftentimes you're selling a parcel of water that enters the system, and the buyer is pulling a different parcel of water from that very system, much like perhaps electricity. But in many cases, those water rights holders are in fact disconnected from the larger network. So, for example, it's my understanding that the Marin Water District, which received quite a bit of rainfall in the last couple of storms, in some cases over 20 inches in a 20 to 48-hour period, is that they're nearly at what they would consider normal for this time of year. They're at 80% of normal, where the rest of the state is somewhere around 30% of normal. They're receiving phone calls daily asking, can we buy your water? For astronomical sums, $2,000 per acre foot, for example. But because they're disconnected from that distribution network, that even if they wanted to sell it, they couldn't. So it's a bit of a mixed bag. The water market system in California is still in a very nascent stage. There are some that do very well in this market, and then others that find themselves having to pay very steep prices. And I think the Public Policy Institute of California probably has the most complete analysis on that. But it's to suggest that ultimately, if you look at the entire California economy, urban centers are likely to pay much, much more than the agricultural sector. And because of that, there may be some consequences to food prices, which we should also be cognizant of.
And we have a question from the online audience. Are hydroinformatics hydrographs used to communicate with California communities?
Are these hydrographs used to communicate to California communities? I would say that's a bit of a mixed bag. Sometimes if you're looking in the sports page, you'll see something about river stage for salmon fishing. And often it says whether it's up or whether it's down. Increasingly now, because of the drought, you may see something on the front page that's showing that we're at 30% of normal, what have you. The Sacramento Bee does do a fairly nice series of infographics in that respect. I think it would be my hope that in the future we could do something a little bit more synoptic to be able to show something about groundwater, which is a virtual unknown for most of the state. That we could say something about what the future holds, that we have 1 year of water supply or we have 3 months of water supply. I think something like that might be more informative, that just rather than telling me whether the river's up or down.
We have had quite a few talks here about the power grid. Since water seems to be at least as crucial or even more so than power, is there any plans of making sort of a distributed water grid that allows, for instance, taking water out of Marin County and put it where we really need it? What are the plans in that direction?
I might defer to my colleagues about the question of where the state of the network is, having a distributed network for water distribution. I do know, however, that a number of studies have shown that just creating simple interties can actually change the balance of how we manage water. One great example was a study that was done on the removal of Hetch Hetchy, which was to show that the city of San Francisco could still meet all of its water needs even without that dam and reservoir. Now they would pay a lot more money for that water, in fact, because it would have to be treated in some way. Whereas now, because it's a fairly pristine watershed, they're able to get by without doing any sort of treatment. But in order to meet the water needs of the city, to sustain that even without that reservoir. It was just a simple intertie between the San Francisco Public Utilities Commission, the Hetch Hetchy water system, and the Turlock Irrigation District and the Modesto Irrigation District. That was just a simple piece of the infrastructure. So I think building that network is certainly possible. Working out who's going to give water to whom remains a bit of a challenge.
One last question over here.
Thanks, Josh. That was really informative. I wondered if you had some observations, just stepping back a little bit, on the socioeconomic impacts of the drought that is being forecasted. You talked a little bit about its impact on tourism, but looking internationally, people have forecasted that water issues are going to be a huge source of conflict in Africa and elsewhere. And I wondered if more locally in California, if you had some thoughts about how it affects the labor market or the agricultural industry or other kinds of impacts that we should be considering.
Yeah, thank you, Camille. So the question had to do about the greater socioeconomic impacts of the drought in particular. There are a number of studies that have come out of UC Berkeley, UC Davis, University of the Pacific, and elsewhere, and certainly they're forecasting a fairly large hit to the agricultural employment sector. The last figure I saw was that there would be a fallowing of about 500,000 acres throughout the San Joaquin Valley. Oftentimes, each acre receives about 3 feet of water, so that's 1.5 million acre feet, which is is a large reservoir, for example. So some questions have been, well, can't we import water from somewhere else? Well, as it turns out, we are importing about as much water as we can from these other sources, such as the Colorado River and so forth. And so because we're at full abstraction, you might say, fallowing is one economic means by which to balance that. Unfortunately, most of our agriculture today, the high revenue agriculture, is in perennial crops, almonds, pistachios, and so forth. And because those are long-term investments and the trees are in the ground from anywhere from 20 to 30 years, fallowing them is a huge expense. And the startup time, once they get going again, is also a huge expense. And so what we've recognized is that what had been the case in the past with California agriculture in a lot of annual crops is that taking annual crops in and out of production is actually relatively easy. They just don't have high revenue. And so this trend towards high revenue perennial crops has actually created a bit of a water management problem. And because of that, we've had these knock-on effects to local economies. That being said, the latest figures out of the Public Policy Institute of California suggest that of that 80% of the water that's used for agriculture, about 1/2 of that water is used for very low revenue crops, irrigated pasture, for example, alfalfa, etc. And that they envision, if a water market were to come to bear, that some of those low revenue producing acres would actually come out of production as opposed to orchards and so forth. But there's a bit of imbalance as to who's put in perennial crops and those who have land that could be fallowed or spared. And so some suggestions have been made that we may be in an era where we actually need to do land use planning, not just for urban areas, but also for agricultural ones.
Thank you, Josh. It was great talk.
Yeah, thank you.